Okay, I've been using this phototransistor to test the light output of a Joule thief, and the question might arise: well, what kind of response does what kind of response does a phototransistor like this actually give? How good is it? Well, I've got the LED there. I've got my little heat shrink tube adapter to hold the phototransistor at a consistent position with respect to the LED that I'm looking at. Now this LED I'm driving strictly from my function generator, from the Interstate F43 Function Generator, and I'm looking at input to the LED on the scope, and then the output of the phototransistor goes has to be powered, so I'm giving it some power, and then it goes to the other, its output then goes to the other channel of the oscilloscope. So here's where the baselines are. Try to get that with no parallax. So for the purposes of this video, I've moved the channel 1 baseline to the center radical marker on the screen there, and the channel 2 baseline is down here on that radical marker where it normally is, right there. Focus. Okay. Alright, so channel 1, turn that on. So there is, what I've done is I've selected the function generator to produce a positive going triangle wave right there, always above baseline, and it is producing that at right around 3 kilohertz, which is a typical operating frequency. Oh, well, pay no attention to this Joule thief over here. That one's not being measured right now. All we're doing is measuring the function generator driven LED and looking at the response of the photodetector phototransistor. Okay, so here's the input signal. Like I said, here's the baseline, here's the input signal, and we're looking at that at, where are we looking at that at? I got the probe set wrong again. Oh, this probe, the switch is very easy to slip. Okay, so let's put that at 10x. Make sure the probe is at 10x. And then, there we go. Okay, so we're looking at this at 2 volts per division. There's the baseline right there. So we can see we've got total input from the function generator, I'll crank that up a little bit, of about 4 volts. We know that it takes a little over 3 volts or so to turn on that white LED, and in fact you can see the little kink there in the triangle wave of the function generator. So the LED is off and then it's turning on right there, and so there's that little voltage drop from a true triangle, and then there's where the LED, the drive voltage goes below the LED's turn on value, so the LED turns off, and there's the other kink. Okay, so now let's look at what the phototransistor is doing. Alright, there's the phototransistor's trace. Again, its baseline is down there. Okay, so the phototransistor is following the illumination of the LED as it's being driven by that triangle wave. Okay, now I've got about 26 volts input to the collector of the photodetector, and we're looking at that at 2 volts per division on the output there. So the phototransistor is giving us 2, 4, 6, 8, 10, about 10 volts output. Let me make sure that probe is attenuated properly. Yeah, that's at 10x attenuation. Oh, look, it looks like a crown, doesn't it? Anyhow, so as I vary the output of the function generator to change the brightness of that LED, see that? The phototransistor picks it up perfectly. But the thing to notice is that it always turns on right where that kink is, and it always turns off right where that kink is. Okay, so we're giving voltage to the LED, and then the LED turns on and the light rises. Okay, so what if I use a sine wave excitation? Let's see here if I can find one. Okay, there's a sine wave excitation. And again, you can see the little departures from the true sine wave right there as the voltage comes up and turns the LED on. And that is coincident with the rise in the light output from the phototransistor. So I think what we've done here is we've shown that the phototransistor is a reliable, linear detector of the light output of the LED. It follows the light curve of the LED exactly. Okay, so a system like this could be calibrated with known power input to a DC powered bulb, and then you would use a known voltage input to your phototransistor, and then you would get consistent power light output intensity readings that you could then use to measure pulse circuits with. Okay. I'm going to go back to the triangle ramp here because I like the way that crown looks. And then we'll turn down the illumination in the LED. And turn up the illumination in the LED. I don't want to blow the LED. All right, thank you for watching.